Hey, my name's Stan, and in this talk, I'm going to introduce medical imaging information systems. In this talk, we're first going to do a bit of background and then discuss fundamental digital image characteristics, PACS systems, DICOM standards and files, as well as radiation dose structured reports. And this talk is based on Diagnostic Radiology Physics, a handbook for teachers and students, and the essential physics of medical imaging. Medical imaging informatics is a multidisciplinary field of science and engineering that addresses the gathering, transfer, storage, processing, display, perception, and the use of information in medicine. It overlaps many other disciplines such as electrical engineering, computer and information sciences, medical physics, and perceptual physiology and psychology. Our culture uses a number system based on 10, because humans have 5 fingers on each hand, and our number systems basically have evolved from the simple act of counting on the fingers. Computers use the binary system for the storage and manipulation of numbers. You can see in the examples below how binary numbers are represented. Although the binary number system may initially seem counterintuitive, breaking it down into simple examples such as these help to understand the concept. In principle, number systems of any base number can be used. The left image is of the legend William Röntgen, who received the first Nobel Prize in Physics in 1901 for his discovery of X-rays on November the 8th, 1895. The image on the right is a timeless classic, one of my personal favorites. This image of his wife's hand marks the beginning of diagnostic radiology. The bones of her hand, as well as the 2 rings on her finger, are clearly visible. This image would have meant a light bulb moment for anyone seeing this at the time, realizing the enormous implications it could go on to have in the medical field. But maybe William was just one of the greatest romantics of all time. Knowing the significance of this image would make their love eternal by living in the minds of millions of individuals across the globe for centuries to come. So, I see your game, William. Anyway, the technical point relating to the previous slide is that X-ray images used to be recorded with a photographic plate, while in modern radiology, all medical imaging modalities provide for digital acquisition. On the left is a label of a box of X-ray plates dating from around the 1920s, signed by George Brady, who was one of the founders of what would become the RSNA, or Radiologic Society of North America. On the right is a box of dry X-ray plates dating from the early 20th century. Some modalities that followed planar radiography are fundamentally digital in that they require image reconstruction from quantified digital signals. Examples of these are computed tomography, as shown on the left, and magnetic resonance imaging, as shown on the right. In this diagram is illustrated a bit of history around medical imaging informatics. The early 20th century saw the discovery of X-rays by William Röntgen, with images captured and stored on film through manual processes. By the mid-20th century, advancements in imaging modalities like ultrasound and nuclear medicine expanded diagnostic capabilities. The 1970s marked a pivotal shift with the introduction of CT and MRI, laying the groundwork for digital systems. The 1980s and 1990s saw the development of PACS and the DICOM standard, enabling digital storage, retrieval, and sharing of imaging data, while the early 2000s brought integration with hospital systems and cloud-based solutions. More recently, the incorporation of AI and cloud technologies have transformed imaging workflows, focusing on automation, interoperability, and advanced analytics. Individual digital images typically consist of a 2D rectangular array of regularly sampled picture elements, also known as pixels. as shown on the left. When an image or frame consists of a cross-sectional slice through the body, then an additional dimension exists, normal to the plane of a slice. A pixel is then referred to as a volume element, or voxel, as shown on the right. In consumer applications, images from digital cameras are usually 8 bits per channel and encoded with 3 channels of red, green, and blue true color information. Medical imaging applications often involve single channels of information representing a single physical quantity, such as X-ray density, and are visualized as grayscale images. These may be encoded such that lower numerical values are displayed as either dark or light. If color is applied to such single-channel images, it is an artificial pseudo-color palette intended to make subtle differences in intensity more visually apparent. On the right, you can see a chest X-ray in 4 different pixel formats. The number in each pixel is converted into a visible light intensity when the image is displayed on a monitor. What this shows is the degradation of spatial resolution caused by using too small an image matrix. The penalty for using larger pixel matrices is increased storage and processing requirements and slower transfer of images. The largest number that can be stored in a single pixel is determined by the number of bits, or bytes, used for each pixel. If 1 byte, or 8 bits, is used, the maximal number that can be stored in 1 pixel is 255. If 2 bytes, or 16 bits, are used, the maximal number that can be stored is 65,535. What these images show is the degradation of contrast resolution caused by using too few bits per pixel. In a medical image, the encoded pixel values are distinct from the information that describes the characteristics of the pixel data, or what's known as metadata. To interpret the pixel data, the recipient needs metadata that describes the dimensions of the pixel array, the number of channels per pixel, the physical spacing of pixels, the number of bits used to store each sample, the photometric interpretation of each pixel, and so on. These metadata may be stored separately from the pixel data, or more commonly, in a header preceding the pixel data. Together, these constitute a medical image. So let's just establish a few key definitions. Hardware refers to the physical components of a computer or other device, while software refers to the programs which consist of sequences of instructions that are executed by a computer. Applications or application programs perform a specific function or functions for a user, such as emails, word processing, web browsers, and so on. A workstation refers to a computer that's designed for the use by a single person at a time. A workstation is usually equipped with 1 or more display monitors for the visual display of information, a keyboard for the entry of alphanumeric information, and a pointing device such as a mouse. In medical imaging, mass storage devices are essential for managing the vast amounts of data generated. Magnetic disks, like hard drives, are widely used for frequently accessed data due to their high capacity and moderate speed. Flash memory, such as USB drives, is portable and durable, but its high cost limits large-scale use. Magnetic tape remains a cost-effective option for backups and archives, while optical discs, like DVDs and Blu-ray, provide durable storage for moderate amounts of data. Advanced technologies like RAID and automated jukeboxes handle the immense storage needs of modern medical imaging facilities, ensuring reliability and accessibility. PACS, or Picture Archiving Communication Systems, may be a small system that addresses the needs of one department, perhaps involving a single modality, with a modest number of workstations for a limited number of specialized users. More commonly, the term PACS refers to a system that serves an entire enterprise, such as a hospital or a large outpatient facility. A PACS is responsible not only for acquisition, archiving, and distribution, but also management of the workflow and integration with other departmental-wide information systems, such as the Radiology Information System. PACS may also be linked to electronic medical records systems that provides access to a broader range of information about a patient in one facility, or to a longitudinal patient health record system that provides for information to span facilities. Modern PACS uses a web server connected to the internet and a thin client paradigm to allow referring clinicians without access to the medical enterprise network to obtain images and reports over the internet. Users within the medical enterprise have access through local and wide area networks. The RIS, or Radiology Information System, provides the patient database for scheduling and reporting of image examinations through HL7, or Health Level 7, transactions, and provides modality work lists with patient demographic information to the modalities, which allows technologists to select patient-specific scheduled studies to ensure accuracy. After a study is performed, the information is sent to PACS in DICOM format and reconciled with the exam-specific information, or accession number. An emergency backup server ensures business continuity in the event of an unscheduled PACS downtime. Also depicted is an off-site backup archive for disaster recovery and real-time customer care monitoring to provide around-the-clock support. So, why do we need DICOM? Well, a standard was needed as the alternative was neither scalable nor affordable. The need to develop open standards to promote interoperability between equipment from different manufacturers quickly became apparent. The first open standard effort for medical imaging was the ACR NEMA standard, published in 1985. This standard defined a mechanism for encoding the pixel data of the images themselves, together with information about the images in the form of a list of data elements. There was little adoption of this standard at the time, and it was not until 1993 that an extensively revised version of the standard was produced, renamed DICOM, or Digital Imaging and Communications in Medicine. Nowadays, the use of DICOM is ubiquitous, and no manufacturer would be able to market a device that did not conform to the standard. So, DICOM is a set of standards sponsored by the American College of Radiology and the National Electrical Manufacturers Association to enable seamless transfer of medical images and information. It facilitates compatibility across imaging devices, PACS, and networks through standardized formats for imaging objects and services for image storage, retrieval, workflow management, and image presentation. In practice, DICOM compliance must be evaluated for both PACS and imaging devices. Contracts should specify the required DICOM standards. And newer image formats offer better metadata and display capabilities, which enhance the workflow and automation in a hospital. Although initially targeted towards radiology-specific applications, the DICOM standard is not restricted in scope and includes support for other medical specialties such as cardiology, dentistry, endoscopy, dermatology, and pathology. DICOM has also been extended beyond the scope of medicine to include non-destructive testing of aircraft parts, as well as baggage screening and other security applications. DICOM facilitates the interchange of medical images and accompanying information through Information Object Definitions, or IODs, that are modality specific but share a common structure. General modules, like the patient module, record fixed characteristics, while modality specific modules include unique acquisition details. DICOM's information model ensures consistency across images in the same study or procedure by replicating shared data into each image instance, creating self-contained composite instances for seamless identification and interpretation, even when images are separated from the originating system. The intent is that a single image may be separated from other images of the system on which it's produced or stored, yet still contain a full set of information necessary to identify and interpret it. DICOM datasets encode information as data elements, each identified by a unique 32-bit tag and a predefined value representation. Pixel data is treated as another data element without a fixed header or specific dataset order, which requires the full parsing to extract reliably the information from a DICOM file. DICOM instances, such as CT or MR images, are transmitted over the network using services like the storage service class. The combination of a service class and an IOD forms a service object pair, or SOP class, such as the CT image storage SOP class. Before transmitting, the sender and receiver negotiate which SOP classes and transfer syntaxes they support. This ensures compatibility, as some devices may only support specific modalities or formats. Manufacturers provide DICOM conformance statements that list supported SOP classes and transfer syntaxes. Comparing these statements during purchase or installation is critical for ensuring interoperability. Devices or software involved in DICOM communication are referred to as application entities, which facilitate the association and data exchange processes. Health Level 7, or HL7, is the general standard for healthcare communication, complementing DICOM for medical imaging by managing other clinical data through text-based messages. HL7 messages are structured with a message header, segments and fields defined by their position, facilitating tasks like patient identification, admissions, and order entries. HL7 also supports integration with DICOM workflows, enabling modality work lists and more complex use cases through frameworks like Integrating the Healthcare Enterprise, or IHE. IHE defines integration profiles to address specific use cases, enabling seamless interoperability between devices and systems using standards like DICOM and HL7. These profiles eliminate uncertainty for implementers and purchasers by defining actors and transactions, such as scheduled workflows for radiology, portable data for imaging, and radiation exposure monitoring. Originally focused on enterprise-level workflows, IHE now also supports cross-enterprise document sharing to enable secure and efficient interoperability across healthcare organizations. The massive amount of data in radiological studies poses considerable challenges regarding storage and transmission. Image compression reduces the number of bytes in an image or set of images, thereby decreasing the time required to transfer images. When stored or transmitted in uncompressed form, digital images occupy an amount of space proportional to the matrix size of the image. However, images typically contain a significant amount of redundant information that can be represented more compactly. Compression techniques transform data to expose redundancy and encode it compactly using methods like Huffman encoding, dictionary coding, or run-length encoding. Image-specific techniques leverage spatial and color redundancy, such as encoding pixel differences or transforming RGB channels into luminance and chrominance channels. Advanced transformations like frequency or wavelet domain encoding further optimize compression by compactly representing image data. Radiation dose structured reports, or RDSRs, are standardized DICOM objects that record detailed radiation dose information for each imaging procedure, allowing us to ensure patient safety, to provide a consistent format for monitoring and reporting radiation exposure, and to support compliance with regulatory requirements. Shown here is an example of the kind of information that can be found in an RDSR. In this example, a patient underwent an angiographic cerebral diagnostic procedure. These kinds of procedures, which are followed and/or preceded by interventions such as a dural arteriovenous fistula embolization, result in patients receiving high skin doses. The spreadsheet shown on the left was generated by extracting the information found in the associated RDSR, which can then be used as an input to a program that we can use to calculate the peak skin dose. And this demonstrates how important RDSRs are in the clinic. RDSRs are indeed indispensable to the clinical medical physicist, as they facilitate dose optimization and quality assurance, they support cumulative dose tracking, they can be used to generate facility reference levels, automate dose monitoring systems, facilitate integration with other systems, and to enable compliance with regulatory requirements. However, it's important to keep in mind that RDSRs can sometimes contain errors, and on a physics perspective, they're subject to a number of limitations. Thank you for listening. Another reminder that this talk is based on Diagnostic Radiology Physics, a handbook for teachers and students by the IAEA, and the Essential Physics of Medical Imaging by Bushberg. If you have any questions, feel free to get in touch. Thank you.